In last class, we studied how to analyze a circuit using Thevenin's theorem. In this class, we will study how to apply Norton's theorem. Here, this complex network consisting of a voltage source with three resistances are simplified into a single voltage source and a single resistance which is in series. So, this is the Thevenin's equivalent circuit of this circuit. In this, a voltage source VTH, V Thevenin, is coming in series with the Thevenin's resistance RTH. With this simplified circuit, we can easily find the voltage and current in the load resistance. While Norton's equivalent circuit is a current source in parallel with a resistor Rn. This current source is called Norton's current IN, and this parallel resistance is called Norton's resistance Rn. Definition of Norton's theorem. Norton's theorem states that any two-terminal complex network can be replaced by an equivalent circuit consisting of a current source in parallel with a resistance. This current source is called Norton's current IN, and this resistance is called Norton's resistance Rn. Then steps for finding Norton's resistor Rn. First, we have to open circuit that load, then short circuit all voltage sources and open circuit all current sources. Here only this voltage source is there that we have shorted and no current source is there. So looking from here is our Norton's resistor Rn. We can simplify this circuit and find the resistance between A and B, which is Norton's resistor Rn. Next, steps for finding Norton's current IN. First of all, short circuit the load resistor RL. Here RL was coming between A and B. After removing that load resistance, we have short circuited. Then find the value of the current through that short circuited path using Ohm's law, KVL, KCL or any other suitable methods. This short circuit current is our Norton's current IN. Now the Norton's equivalent network will be the Norton's current IN we have found out and the Norton's resistor Rn, which also we have found out. Using this simplified circuit, we can find load current IL using current division rule. See here, this IN is coming and dividing into this branch and this branch. So the current IL flowing through the load is total current, that is IN into the resistance of the other branch Rn divided by total resistance. Similarly, the voltage between A and B also can be found out as V is equal to I into R, that is VL is equal to IL into RL. In example 1, we are asked to find the current in the 10 ohm resistance of the figure shown. We will use Norton's theorem to solve this problem. For solving it using Norton's theorem, we have to find out Norton's resistor Rn and Norton's current IN. First, we will find out Norton's resistor Rn. To find Norton's resistor Rn, first we have to open the load resistor RL. Here we have opened this load resistor. Next, we have to short circuit our voltage sources and open circuit our current sources. Here two voltage sources are there to short. One is coming here and one is coming here. There is no current sources, so no question of opening it. See here, this 40 ohm is short circuited. So the effective value coming here will be 0. This 50 ohm is in parallel with 20 ohm. Therefore, Rn is equal to that 50 ohms in parallel with 20 ohm, which is equal to 14.28 ohm. This is our Norton's resistor. Next, we will find Norton's current IN. After removing this load resistor, A and B are short circuited. As 50 ohm and 40 ohm are connected in parallel, we can interchange it by bringing this 50 to this side and 40 to this side. This will not make any changes in the circuit. See, this 50 ohm came here and 40 is here. Find the value of that current through that short circuited path using any of the laws like Ohm's law, KVL, KCL or any other methods. This short circuited current is our Norton's current IN. Here we will apply KVL. For applying KVL, first we have to mark the meshes. Let this is mesh 1 and this is mesh 2. Then let I1 is the current flowing in this direction in mesh 1 and I2 is the current flowing in the second mesh in this direction. Then we have to mark the direction of currents in these resistances. See, as I1 is flowing in this way, current is entering here, which we will mark it as plus, and leaving here we have to mark minus. In this one, current is entering here plus and here leaving minus. In this mesh, current is entering here plus and leaving here minus. Applying KVL to mesh 1, see, as current is flowing in this direction, here it is rise in potential plus 50, then here it is plus to minus, that is voltage drop minus I into R, 50 into I1. Then in this resistance, voltage drop is there, so minus 20 into difference of these two currents, I1 and I2. As we are in mesh 1, I1 is to be written first. I1 minus I2 is equal to 0. Simplifying this equation, we will get 70 I1 minus 20 I2 is equal to 40. Let this is equation number 1. Applying KVL to mesh 2, here it is rise in potential as we are going like this. So plus 10, then in this 20 ohm plus to minus, so minus 20 into difference of these two currents. As we are in mesh 2, I2 is to be written first. I2 minus I1 is equal to 0. Simplifying this one, we will get minus 20 I1 plus 20 I2 is equal to 10. Let this is equation number 2. Solving equations 1 and 2, we will get I1 is equal to 1 ampere and I2 is equal to 1.5 ampere. Here see, this I2 is the current flowing in this branch also, that is I2 and IN both are same. Therefore, Norton's current IN is equal to I2, which is equal to this 1.5 ampere. Here we got Norton's resistance Rn is equal to 14.28 ohm, that is Rn is equal to 14.28 ohm, and IN we got as 1.5 ampere, 1.5 ampere. Now the Norton's equivalent network is like this. Here IN is 1.5 ampere and Rn is 14.28 ohm. In the question, the load resistance is given as 10 ohm. We can find load current IL using current division rule. That is, this IL is equal to IN, that is the total current, into these two resistances are in parallel. So as per current division rule, current through this branch, our load resistance IL is equal to total current IN into resistance of the other branch divided by total resistance. So IL comes here, IN is 1.5 into Rn, that is 14.28 divided by 14.28 plus 10, which is equal to 0.88 ampere. We can find the voltage across the load resistance, that is between A and B. V is equal to I into R, that is VL is equal to IL into RL. This is equal to IL 0.88 into RL 10 ohm. This is equal to 8.8 volts. In this example, we are asked to find the Norton equivalent circuit of this given network for calculating current through this 10 ohm resistor, which is connected between A and B. First, we will find out Norton's resistor Rn. To find Norton's resistor Rn, first of all, we have to open the load resistor RL. Here 10 ohm is the load resistance. Then see, here it is open circuited. Next, what you have to do is you have to short circuit all voltage sources and open circuit all current sources. Here the voltage sources are this 10 volt and 20 volt, that we have to short circuit. See, this 10 volt is short circuited here and 20 volt is short circuited here. Now we can find Norton's resistor Rn by simplifying this circuit. See, looking from here, 6 ohm and 1 ohm are in parallel, which is in series with 2 ohm, and that is in parallel with 3 ohm. So Norton's resistor Rn can be written as 6 ohm in parallel with 1 ohm, which is in series with 2 ohm, and this is in parallel with 3 ohm. This is equal to 1.46 ohm. So our Norton's resistor is 1.46 ohm. Next we will find Norton's current IN. To find Norton's current IN, first we will short circuit the load resistor RL. See here 10 ohm connected between A and B is removed and points A and B are short circuited. Then Norton's current is the current passing through that short circuited path. We can use Ohm's law, KVL, KCL or any other suitable methods. For applying KVL, first we will mark the meshes. Let this is mesh 1, this is mesh 2 and this is mesh 3. Then we have to mark the mesh currents. Let this is current I1 flowing in mesh 1, current I2 flowing in mesh 2 and this is current I3 which is flowing in mesh 3. Next we will mark the direction of current flow in the resistances. In this mesh, current is flowing in this way, so it is entering here which we will mark it as plus and leaving here which we will mark it as minus. In 1 ohm resistance, it is entering here and leaving here. See, in this mesh, in 2 ohm current is entering here and leaving here. In 3 ohm current is entering here, leaving here. In 1 ohm it is entering here and leaving here. Applying KVL to mesh 1, as current is flowing in this way, here it is rise in potential, so plus 10 volt. Then in this resistance, voltage drop is there as it is flowing from plus to minus, that is minus 6 into I1. Here in this mesh, it is flowing from, I1 is flowing from positive to negative, so minus 1 ohm into difference of I1 and I2 as they are in different directions. So we have to take the difference of I1 and I2. As we are in mesh 1, we have to write I1 first, then I2. This is equal to 0. Simplifying this equation, we will get 7I1 minus I2 is equal to 0. Let this is equation number 1. Now applying KVL to mesh 2, here current is flowing in clockwise direction. In this 2 ohm, current is flowing from positive to negative, so voltage drop is there, that is minus 2 into I2. Here also it is from plus to minus, so in this resistance voltage drop is there, so minus 3 into difference of I2 and I3. As we are in mesh 2, I2 is to be written first minus I3. Then next voltage drop is in 1 ohm, as it is voltage drop minus 1 into difference of I2 and I1. As we are in mesh 2, we have to write I2 first minus I1 is equal to 0. Simplifying this equation, we will get minus 1 I1 plus 6 I2 minus 3 I3 is equal to 0. Let this is equation number 2. Now applying KVL to mesh 3. In this mesh, as current is flowing in this way, here it is positive and this is minus. In this resistance, voltage drop is there as it is going from plus to minus, so minus 3 into difference of these two currents as they are in opposite direction. As we are in mesh 3, I3 is to be written first, I3 minus I2. Then here fall in potential is there, as it is fall in potential positive to negative, minus 20 is equal to 0. Simplifying this equation, we will get 3I2 minus 3I3 is equal to 20. Let this is equation number 3. Solving equations 1, 2 and 3, we will get I3 is equal to minus 13.17 ampere. See, here we can see that I3 is the same current as this short circuited current, that is it is equal to IN. Therefore IN is equal to I3, which is equal to minus 13.17 ampere. So we got IN is equal to minus 13.17 ampere and Rn is equal to 1.46 ohm. 1.46 ohm. Now the Norton's equivalent network is Norton current IN in parallel with Rn. Norton current we got minus 13.17 ampere and Norton resistance we got as 1.46 ohm. See, here we assumed Norton current is flowing in upward direction, but actual value we got negative. That means actually the Norton current is flowing downwards. As it is flowing downwards, this load current also will be flowing in the opposite direction, flowing upward. This is 13.17 ampere flowing downwards. This is 1.46 ohm. Load current is 10 ohm, which is given. Now we can find the load current IL using current division rule. that is load current IL is equal to total current, that is this Norton current, into the resistance of the other branch divided by total resistance. Therefore, IL is equal to IN 13.17 into 1.46 divided by total resistance RN, that is 1.46 plus 10. This is equal to 1.67 ampere, which is flowing upwards. In example 3, we are asked to find current through the 10 ohm resistance in the figure shown. See here, as we are asked to find the current through this 10 ohm resistance, our load resistance is this 10 ohm, which is connected between A and B. Here we will apply Norton's theorem. For drawing Norton's equivalent circuit, we have to find out IN and RN. First, we will find out Norton's resistor RN. To find Norton's resistor RN, first we have to open circuit the load resistor, this RL. See here, between A and B, we have open circuited that 10 ohm resistance, which is our load resistance, and what is the resistance coming in between A and B is the Norton's resistor. Next, what we have to do is, we have to short circuit all voltage sources and open circuit all current sources. This is the voltage source which we have short circuited here, and this current source is open circuited. In this circuit, looking from here, this 5 ohm and 15 are coming in series, which is in parallel with 1 ohm. Therefore, Norton's resistor, which is coming between A and B, is Rn is equal to 1 ohm in parallel with that 5 ohm and 15 ohm, which are connected in series. This is equal to 0.95 ohm. Next, we will find the Norton's current. To find Norton's current IN, first we have to short circuit the load resistor RL. Load resistor was connected between A and B, which is short circuited, and the current flowing from A and B is our Norton's current IN, which is that short circuited current. We will then find the value of that current through that short circuited path using Ohm's law, KVL, KCL, or any other suitable methods. For applying KVL, first we have to mark the meshes. Let this is mesh 1, this is 2, and this is 3. In mesh 1, let the current is flowing in the clockwise direction. Here also current is in clockwise direction. Here also current is in clockwise direction. Then we will mark direction of current flow in each resistance. As current is flowing in this way, entering point is marked as positive, then leaving negative. In 5 ohm also, here it is entering plus minus. Applying KVL to mesh 1, in this battery, rise in potential is there. So, plus 2. Then in this resistance, voltage drop is there. As it is voltage drop, minus 1 into I1. This is equal to 0. Therefore, solving this equation, we will get I1 is equal to 2. Let this is equation number 1. As we have marked earlier, here the current is I1, which we have already found out. Here it is I2 and here is I3. As these two meshes form a super mesh, the equation can be written as voltage drop is there in 5 ohm. So, minus 5 into that mesh current I2, then coming here minus 15 into I3 is equal to 0. Let this is equation number 2. See, while looking between meshes 2 and 3, this I2 and I3 are in opposite directions, and in this branch current is 4 ampere. That means the difference of currents in these two meshes is 4 ampere. So we can write I2 minus I3 is equal to 4 ampere. Let this is equation number 3. Solving equations 1, 2 and 3, we will get I1 is equal to 2, I2 is equal to minus 3, and I3 is equal to 1 ampere. So this IN is the difference between I1 and I2. Therefore, Norton's current IN is equal to I1 minus I2, which is equal to 2 minus 3, that is 5 ampere. So we got Rn is equal to 0.95 ohm and IN is equal to 5 ampere. Rn is equal to 0.95 ohm, IN is equal to 5 ampere. Now the Norton's equivalent network is like this, where IN is 5 ampere and this RN is 0.95 ohm. RL is given in the question as 10 ohm. Now we can find load current IL using current division rule. That is, this load current IL is equal to, as this is a current divider, the total current comes and divides into 2. So IL is equal to total current, that is IN, into resistance of the other branch RN. In this case 0.95 divided by the total resistance. This is equal to 5 into Rn. 0.95 divided by 0.95 plus 10, which is equal to 0.43 ampere. In example 4, we are asked to draw a Norton's equivalent circuit for the given circuit. So you can see that here in this 3 and 4 are coming in series. The given circuit can be simplified and redrawn as like this. See, this 3 ohm and 4 ohm are drawn like this. See, actually these are in series. As they are in series, we can add it and further simplify like this. This becomes 7 ohm. Now we will find out Norton's resistor Rn. To find Norton's resistor Rn, here we have to find the Norton's resistor Rn between A and B. For finding Norton's resistor Rn, we have to short circuit all voltage sources and open circuit all current sources. So here there is no voltage sources, only one current source is there, that we have to remove. We will be removing this current source. Now our circuit becomes like this. This current source is opened here. Remaining are these resistances, and between A and B is our Norton's resistor Rn. As these points are open circuited, this 5 ohm is having no effect in this circuit while calculating Rn. Here 2 ohm is coming in series with this 7 ohm, and that will be in parallel with 5 ohm. 2 ohm and 7 are series, means 2 plus 7, which is in parallel with 5, that is equal to 3.21 ohm. So this is our Norton's resistor, which is equal to 3.21 ohm. After finding this Norton's resistor Rn, we will find Norton's current IN. For finding the Norton's current between A and B, we have to short circuit the points between which Norton's current is to be found out. Norton's current IN is the short circuit current which is flowing from A to B. So here, as this short circuited path is in parallel with the 5 ohm, the effective resistance here becomes 0, like this. See, from A to B it is short circuited, which is the Norton's current. Now we will find the Norton's current IN, which is that short circuited current. So you can see that 25 ampere current flowing in this way is passing through this 5 ampere resistance, and here it is splitting up into 2 branches, one which is containing 2 ohm and 7 ohm. So we can use the current divider rule for finding the current passing through this branch. Therefore, IN is equal to total current, that is 25 ampere, into the resistance of the other branch, that is this 2 ohm, divided by total resistance 2 plus 7, which we will get as 5.55 ampere. Therefore, we got IN is equal to 5.55 ampere and Rn is equal to, see here we got Rn is equal to 3.21 ohm. Now the Norton's equivalent network is like this, that is IN is equal to 5.55 ampere and Rn is equal to 3.21 ohm. I think this class also might have been useful to you. If you found any difficulty in understanding any terms used in this class, you can refer to my previous classes, the links of which are given below. Thanks for watching. Please like it, share it and subscribe it by pressing the bell button, so that you will be getting all the notifications of my future videos also. See you next time. Bye.